Let's start. Uh, today we have the sixth talk on our Transpacific Colloquium series. I'm happy to present our colleague, Professor Meera Parish. Uh, she is one of the leaders in many body theory in cold atomic and condensed matter physics. Meera has made her PhD at the University of Cambridge in 2005, and after two postdoctoral positions at Princeton in the United States and again in Cambridge, she became a faculty of the University College at London in 2011, and in 2015 she have made a great decision to move to Monash, and we enjoy her here, where she has recently become a professor and ARS Future Fellow. And Meera has also get a number of prestigious fellowships, including the Maxwell Medal and Prize of the Institute of Physics of United Kingdom. Okay, before we start in a talk, let me quickly remind you that questions, of course, are welcome. They welcome through the chat, and the speaker will make one or two stops during the talk for questions, and you will have also opportunity to ask questions at the end. Okay, please, Meera, please free to start, and we will enjoy the talk.
Yep, thanks, Dimitri. Can you see my shared screen? Yep. Okay, great. Thanks. It's a pleasure to be giving this colloquium, even if it's virtual and I'm talking to a screen, but it's a really great opportunity to tell everyone a bit about what I've been doing. So what I wanted to tell you a little bit about is the work I've been doing on impurities in a Fermi sea. And so let me first tell you what I mean by that, and then why would you care? Why would you bother? So firstly, what I'm imagining is you have a Fermi sea, so a gas of fermions characterized by some Fermi energy, so density. And what I want to ask is what happens if I put in a single impurity or a very small number of impurity atoms or particles in this gas? And moreover, what happens if I turn on the interactions between these impurities and the Fermi gas? So it could be very strongly interacting. And I want to argue that this is actually a very fundamental and ubiquitous problem in physics. It shows up in all sorts of places, not just in the quantum gases, cold gases that I'm going to be focusing on today. It even shows up, funnily enough, in neutron stars. There are some very interesting questions about what happens when you have a small number of electrons in neutron matter and in neutron gas. And this could have implications for even the equation of state of a neutron star. It shows up even in the behavior of semiconductors. So what happens when you look at light absorption in a semiconductor? So here, what happens if you shine light on a semiconductor with a doped semiconductor where you have lots of electrons, you create this electron hole pair, this bound state. And this is once again like the impurity here. So in a Fermi gas. And so then you have, by looking at the absorption peak structure, this also can be understood in terms of this impurity problem. And actually, this is something that even Dimitri himself has worked on. So I want to emphasize this is very much a ubiquitous and fundamental problem. And what's nice is that you can do very controlled experiments and controlled kind of investigation of this problem in cold atomic gases. And this is what I'm going to tell you about today and what we've learned about it. So there's been very many nice experiments around the world, around in Europe and the US, MIT and Innsbruck and so forth. And in what's called the Fermi polaron. So that's just the impurity in a Fermi gas. Now, what's particularly interesting is you can use it to investigate the concept of what's called the quasiparticle. So what we're trying to understand here is how this impurity changes its properties, changes its behavior when you insert it, when it's interacting in this medium, in this Fermi gas. And you can think about it in a kind of quasi-particle way, where I'm imagining that it dresses itself with excitations, or dresses itself with particles of the medium to form what looks like a quasi-particle, but it now is no longer just the bare impurity. It's also got parts of the medium attached, and and you can think of it in some sense like I mean, this is this nice picture from a textbook here, but think of it, if you had analogously a horse running through a desert, and it stirs up all its dust. You can imagine this object moving through the desert, the dust and the horse, as being like this quasi-horse. So we're thinking of particle-like objects, but are not necessarily the original bare particle. Okay, they involve excitation, many-body excitations. And this is something that also goes beyond the impurity problem. It's really a way in which we can also characterize many-body systems generally, where the excitations of a many-body system can be particle-like. So they have this quasi-particle, and they have these quasi-particles showing up again. And in particular, one famous description of a many-body Fermi system is the so-called Fermi liquid, which involves, because it was deeply kind of, involves these quasi-particles, this concept of the quasi-particle in this Fermi system. So what we can also think about is, can we look at scenarios which actually go beyond this usual description of this Fermi liquids description? So I'll come back to that a bit later on. So let me start in this talk. I'll first walk you through how do we actually go about probing the physics of this impurity, or this Fermi polaron in the cold atomic gases. So these are these trapped, very dilute cold atomic gases. And how do we actually go and probe them, with light? So there's radio frequency spectroscopy. And then I'll move on to actually, what does it tell us about the nature of this Fermi polaron, or this dressed impurity, this quasi-particle? How does it evolve with temperature? And can we learn anything actually even about the different types of impurities, dressed quasi-particles, polarons? So let me start then with the probes. I don't know, probably, are there any questions at this point? Or shall I continue on a bit? Okay.
Do we have any questions so far? Okay.
It's very early on in the talk. So.
Not yet.
Okay. Right. So how do we actually probe and interrogate this impurity problem? So what typically you can do? There are two scenarios in this the so-called spectroscopy. There's these sort of spectroscopy protocols. So what we're imagining is, okay, we could either start with an impurity in some particular state. So this could be an atom in a particular spin state. Okay, so it's surrounded by atoms of another type, or so for this, for instance, to give a realistic example, this could be, for instance, a potassium atom in a particular spin state surrounded by a gas of lithium atoms, just as an example. And what you can do is you can apply a radio frequency electromagnetic pulse to this and flip the spin into another spin state of this impurity. And this can be, you've engineered it so that this spin state is actually strongly interacting with the surrounding fermions. Okay, so this so-called injection scenario. So you've injected an impurity into a strongly interacting state. What you can do then is you can actually ask, if I do this, what is the how much of these impurities do I transfer into this state? For a given frequency of the applied field. Okay, so you drive it into this state, and then you ask, what's, as I vary the frequency of my pulse, how much of these impurities do I transfer? And you can also go back the other way. You can start with a gas impurity system in equilibrium, strongly interacting, and then you can eject it into the non-interacting state and ask the same question. So this transfer rate gives you access to what's called the spectral function, but really it's just giving you access to the energy states of your system, your impurity system, and how well it resembles, or how much it resembles, the non-interacting state, if you like. So let me show you one example. So here is an example injection spectrums that are measured back several years ago, back in 2012 in Innsbruck. So let me walk you through here. So we have the energy. This energy on this axis is the frequency of the applied field, the radio frequency. So you can think of it as the frequency of the light, or the radio frequency pulse. Okay, so that's the frequency. And then along this axis is the interactions. So you can vary the interactions between this impurity and the surrounding fermions. And so these are short, I should say these are short range interactions. So they can be characterized by just a scattering length, A. So it's just a way of, you should just think of this as a way of characterizing the strength of the interactions. So, so out here on this side, so on the right side here, you have effectively very weak interactions, so negative scattering length, very weak interactions. And more importantly, there's no two-body bound state of between the impurity and the fermion. And then while on this side here, on the left-hand side, you have now you have strong enough attraction that you can actually form a two-body bound state. Once again, involving an impurity and a fermion. Okay, so those are the sort of two. So you think of attraction as increasing from right to left here. And what you can see now here is that you have actually these two branches. So on this side here, you have this branch at negative energies. And then on this side, you have one at positive energies. And so the way you can, and you notice, I mean, these two branches basically have they have a large signal here. So you have a large transfer rate just here. And then you have this continuum in between here. Okay, and so the way to think about it is you have something that where a so-called attractive quasiparticle, where the impurity is sort of pulling in fermions around it. It's increasing its density here, whereas addressing itself with more density. Whereas on this side, actually, you have what's called a repulsive quasiparticle, where it's actually pushing particles away, pushing the fermions away. And the way you can think about this is, okay, so this is a quasiparticle that eventually becomes the two-body bound state as you go along this axis, as you increase the attraction. Whereas here, this one, as you go along here, you can imagine, say, lowering the density of the gas as you go along here. This actually becomes just the bare unbound particle. So you have these two branches that are, in some sense, like a many-body version of a bound particle, a bound state and an unbound state, plus this continuum in between. Okay, and so that's basically, if you inject it and you just see the whole spectrum when you do this. Now, if you try and eject it, so you start with the interacting state and then you try and sort of eject a fermion, eject a impurity out of that interacting state. Okay, so now what's happening here? Okay, so this is, if I say this is for a fixed interaction now. So this is from an experiment just from a year ago, where if you sit now right at this point here, this is where the scattering length diverges, and sort of essentially it's basically where you start, you initially form this two-body bound state. But okay, but it's just sitting right in the middle of this diagram here. Okay, now what you see actually is that you only have a strong weight at negative energies here. Okay, right? And then eventually, as you increase the temperature, so this is a plot as a function of temperature, you find that it actually starts to head towards higher energies. Whoops, I'm sorry. Okay, apologies. Okay, so you see that actually this spectrum, you have this sort of similar, you actually only have one branch in this case, and it changes as a function of temperature, right? So you have a lower branch so you have this kind of basically this attractive branch that actually shifts to higher energies as you increase temperature. So what I want to point out here is that actually, okay, so you probe the spectrum in this manner, this energy spectrum, and actually what we found was that these are actually these two different ways of measuring the energy spectrum are related. So this ejection spectrum here, as a function of frequency, is related to the injection spectrums, say along here, just by a simple the Boltzmann factor. So this is just this frequency divided by temperature here, this exponential, and also an additional factor here, which is just encodes actually the energy difference, or the free energy difference between the interacting and non-interacting states. So what this tells you then is that the ejection, by probing either one of these, injection or ejection, you're measuring the same thing. In ejection one, you're actually, this Boltzmann factor is essentially just picking out it's suppressing the higher energy states, and it's just picking out the lowest branch. But this, as you increase the temperature, now you start to probe the higher energies. So that's what you're seeing here. But also, actually, you can actually learn something about the thermodynamics, not just the energy spectrum, but even the thermodynamics of the impurity fermion system, from looking at comparing the two, the heights of these two spectrum. Okay, in practice, it's probably hard to do an experiment, but still, nonetheless, there's this thermodynamic quantity that's also appearing in what you think is just a dynamical probe here. Are there any? Okay, that was quite a lot of information. Is there any questions at this point?
Is this relation between ejected and injected, is it exact, or any approximations have been done?
Yes. Okay. No, that's a
derivation.
So this is exact for the case where you have a very small number of impurities. So actually, this would be exact in the limit where you have a vanishingly small density of impurities. So as you increase the density, at some point, this relationship will fail. But it's really assuming that you have just a very small number of these impurity particles.
So the argument is, if you have a quantum system, you add an impurity, and if you probe impurity, you could get the free energy of the quantum system.
Yes. Mm-hmm. So the other assumption we've made here is that we're in thermal equilibrium in both cases. So the non-interacting system we assume is in thermal equilibrium with some well-defined temperature. Also, for the injection case, and the ejection case, we're assuming the initial interacting system is also in thermal equilibrium with a well-defined temperature. Yeah.
Thank you. Any other questions? Probably not yet.
Not yet. Okay. I haven't lost too many people. Okay. All right. So that's one way. So here in the previous slide, we were assuming that we just transferred a small amount. So we applied our radio waves and then just transferred a small number of impurities, or flipped a small number of impurities spin. Now, what about if you just turned on kept the just continuously drove the system, so you kept the radio waves on in this scenario, so you didn't actually just transfer a small amount and then switch off, but you actually just kept the drive on. So what happens in that case? So you're driving it between these two different spin states of the impurity, remember? Now, if I didn't have the medium, so I didn't have any fermions, I just had a gas of these, a small number of these impurities, and I was just driving them between their different spin states. What I would find as a function of time, I would find that there would be an oscillation between the two different spin states, as you can see here with this gray curve here. So you just, by driving it, you're just executing you're just shifting the impurities back and forth between the two different spin states. These are called Rabi oscillations. Just like this is sort of just like in an ordinary kind of two-level system or a spin system, where you're just flopping between the two different up and down states. Now, what happens if you have a background medium now? Now you imagine that one of these spin states strongly interacts with, or in principle arbitrarily strongly interacts with the Fermi gas. Now, actually, what you see is sketched out in these curves, these other colored curves here, where you see two things. One is that the frequency shifts of is different from the bare frequency of these oscillations, the gray curve here, and also that now you get some damping due to having the background. So you get some kind of decoherence. You no longer get these coherent oscillations. And what you can show, actually, what's interesting is you can actually learn something about what's happening when you measure these from these oscillations. You can show that actually the change in this frequency that you see is actually just gives you a measure of the overlap between the original sort of non-interacting state here and the interacting state. So it's actually the square root of this overlap here. So that multiplied by the Bayer frequency actually gives you this new frequency here. So typically you see that this frequency, so this overlap is less than 1. So this frequency actually gets is reduced. So you get these slower oscillations that you see here. But you can also, we can also actually understand how this damping occurs. And that's just by coming back to our spectral function that I was showing you before. So here, once again, what I've shown you here now is just a slice of the spectrum, of the transfer rate of the spectrum for a given interaction strength. Okay, so or rather, here this is the spectrum you would expect for a non-interacting system, non-interacting impurity, and there you just had it's quite a boring, just a delta function of strong peak around 0. Because you just have this well-defined bare particle. This is what it's telling you. You have this nice perfect overlap, more or less, with a non-interacting impurity, and there's no real energy shift. But now, if you come to the spectrum of the interacting case, so here's as a function of frequency. So here we're looking at the case where I've just picked a slice where now I have the repulsive quasiparticle branch. So there was this branch, if you remember, that where you were shifted to positive energies here. So we have a shift in the peak, but now we also get this broadening here. And so we have this many-body system. We now no longer have this well-defined bare kind of particle. We now have a sort of an approximate particle-like peak here with this broadening, which gives a measure of just essentially how well or how long it lives as a kind of quasi-particle here. And so now what we find actually, what we've been able to show is that this damping that you see here is basically connected to this lifetime of this interacting state here. So this damping of this oscillation is basically the width of this peak in the spectrum. So this is an approximate expression, but it seems to hold up quite well. Okay, and then we also found some correction to the actual frequency that involves this damping. Okay, but that's in some sense a more minor point. The point is we now can really understand how this damping and how this frequency shift comes about just from looking at this spectrum here. Okay. Okay, shall I ask now if there are any burning questions about this?
Do you have any questions?
Feel free to write in the chat if that's easier.
Oh, for this spectral function, it doesn't have only a peak, but it has long, coherent, uncoherent tail on the left.
Yes.
Does it have any manifestations?
Well, let's see. So I guess it does actually have. It will affect some of the. Yes. Okay. Hang on. Yes, I think it essentially it will affect how you damp it. So what this approximate expression would give you is it would tell you that you would just damp to 0 essentially, whereas actually the other parts of the spectrum, I think including this additional continuum we were talking about, essentially kind of give you like a I don't know if you would call it a revival or such, or it essentially means that you, instead of actually damping to 0, you damp to some finite value here, I think. So it is. So you're right that there's a bit more complexity associated with the spectrum that's not captured in this simple expression, but but I think it's essentially. It's something we don't have to worry about if we're just looking at the damping and just looking at the frequency. But yes, it does in principle have effect, and a small effect at least.
Okay, I see. We also have question from the Variational fields.
Yes.
So please go forward.
Yes, also gonna ask, I think you answered at least part of this question already, but for this expression you've got on the slide,
Yes.
what approximations were used?
Yes. So yes, so I sort of half answered yes with Dimitri's question, but yes, the other so we assumed that we could just how would I put it? We focus, say, on just the part that overlapped with the non-interacting state. So we only looked at the parts of this oscillation where it would have some finite overlap with the non-interacting state. But in principle, there are other contributions that we should take into account. Higher sort of other contributions to the oscillations that are also there and also mean that we don't get this damping to zero, but we actually go back to something finite. I don't know if that answers your question. It's probably I need to write it down, but yes, we are missing something, additional terms where they don't just have a straightforward overlap with a non-interacting state.
Yeah. Okay. Thank you.
Yeah. All right.
Okay. I think no questions. No other questions anymore.
Okay. All right, yeah, actually, it's funny you're asking about the approximations, but now, well, this actually, yeah, so that what I just showed you was approximations basing about how to approximately connect it to the spectral function. Now what we can try and do is essentially do a little bit more of a sophisticated approximation. I won't go into too many of the details, sorry, I'll just give you a general flavor of how we actually go about modeling these different scenarios in this problem, because it's kind of cute, because what we do is we model, well, we take a variational approach for the impurity operators. This could in principle include both the two types of spin states. So it's a time-dependent variational approach, time-dependent operator. So if I do it in pictures, okay, so this is how it would be in the mathematics. But essentially, what we do is we use a variational approach, which includes, say, essentially the part which has a good overlap, the non-interacting part, if you like, and like with the good overlap with the non-interacting state. So this is like the unperturbed impurity in Fermi C. And then we include one where the impurity just creates an excitation of the Fermi C. And that's it. So in principle, we should, if we had the exact case, we should have an infinite number of excitations of the Fermi C, not just this single one here. But the approximation we use is so we have a variational one which only includes a single excitation. So that's the main point. And okay, it might seem like a fairly drastic one. We've cut out most of the excitations, but what you can actually show is that we know actually when this is a good approximation. We know that it's actually exact if you have very short times, because if you're imagining you've just, say in these Rabi oscillations, you've just introduced the impurity at short times. We know that it takes time to create excitations of the Fermi C. So initially at short times, you do essentially only have one excitation. So we know that this works. And actually, funnily enough, at high temperatures, so temperature has the effect of actually destroying a lot of correlations between your impurity and your Fermi gas. So you can actually also get away with something where you have very few excitations involving the impurity and the Fermi gas. Okay, so that's I don't want to go into too many details, but that's the main idea. We do this approximation, try and model these. Now, okay. So I've talked about the probes. I've told you a little bit about how we actually model that, with this just including a single excitation when we model the interactions between the impurity and the Fermi gas. Now I just want to tell you a little bit about what we can learn from looking at the experiment, looking at what they find, and also comparing it with our theory. Okay. So as I mentioned before, you can actually extract the difference in free energies between the case where you have the impurity interacting with the Fermi C and the one where it's not interacting with the Fermi C. And this can be at any temperature in principle. I'm just assuming that this is the case at some given temperature. And that you can get from doing these spectroscopy in principle. I think in practice maybe it's hard, but in principle, and theoretically it's easy for us to do, relatively. So I say this confidently because I'm not the one actually doing the calculations. And then there's another actual interesting quantity that's quite popular in the cold atom context, and I think is generally an important quantity for any kind of system where you have short range interactions, is what's called the contact. Okay, so this is basically another type of thermodynamic quantity where it corresponds to the derivative of this free energy with respect to the interaction. So this is the inverse scattering length here. So it's very much like, you have all these other parameters like other derivatives of the free energy. So you have, say, the derivative of the free energy with respect to temperature, or the derivative of the free energy with respect to chemical potential, and these all correspond to specific quantities like density and particle number and so forth. So this is very much the same thing. It's like another thermodynamic quantity which you can get from taking the derivative of a free energy. But now we have the interaction. And this has a physical meaning that it corresponds to essentially like okay, so how do I describe it? It gives you a sense of the correlations of your system, or if you like, the density of fermions close to your impurity. So if the contact is large, it's telling you that there's more kind of fermions clustered around your impurity than if this is smaller. So obviously, attracted to it. So obviously, if you had zero interactions, the contact should be zero. And zero interactions between your impurity and the Fermi gas. And as you increase the attraction, this contact will increase. Okay. Now, okay, let me tell you the surprising thing that was found in the experiment, which was that if you look now, if you sit at this point at unitarity, so remember this point at unitarity, that's just the point where it's a particular interaction. It's the point where the scattering length goes to infinity. Okay, so this is a special point because essentially the scattering length drops out of the problem. It corresponds to the point where you first, have a bound state in your system, or a bound state appears. And actually, while we're on this subject of unitarity, it's believed to be the scenario in a neutron star, actually, neutron matter. That's roughly a case where you have unitary interactions like this, infinite scattering length. Okay, but that's an aside. Okay, so there's a lot of interest in this particular interaction. Now, what's interesting, if you sit at this interaction and you look at if you look at, say, they measured the contact as a function of temperature. Say this was in the case of a lithium impurity in a lithium gas, so equal masses of the impurity in the fermions. What you find is actually as you increase the temperature, the contact actually goes up, and then it goes down at higher temperatures. Okay, and I just want to emphasize this is actually rather surprising, because you would naively have thought that as you increase the temperature, you shouldn't, make the system more kind of strong, I don't know if you want to call it quantum and such, but you shouldn't make it more interacting. You wouldn't think that the temperature would increase attractions between your impurity and your Fermi gas. You would think that it should actually decrease it, which is what it does at high temperatures. So it was actually kind of surprising that, why does it actually go up initially? And what's interesting is we can actually go ahead and we can do our theoretical calculation, approximation I mentioned previously, and we find exactly this behavior, this non-monotonic behavior where it initially goes up and then it goes down. And we can also see this actually, if you look at this blue curve here for the free energy, we can also see this kind of reflected in the free energy. The free energy goes down and then it goes up. So, or rather, it goes towards zero. So you would also expect the free energy to go to zero at high temperatures. It will resemble a non-interacting system. All right, hang on. Okay, so are there any questions at this point before I explain? Well, okay, I'll hopefully answer the question about why it's doing this now. But are there any other related questions of this at this point? Like, what is about the contact? Is this kind of clear?
Any questions?
Yeah.
Not yet.
Not yet? Okay. Right. Okay, and I should mention, sorry, there's also, if you do there are also calculations of just a few particles which also show this behavior. So so this is telling you essentially, the way you can think about it is, this is telling you that there are excited states in your system that are essentially like a more attractive, more interacting, if you like, in some sense. And okay, if we come back now to the spectrum, what's happening here? Okay, so this is my schematic spectrum. So here's energy on this axis, and this is the interactions. And we're sitting here, right, at zero, or infinite scattering length here. And so this is just essentially a zero temperature spectrum, say, yeah, like what I was showing you before. So you have your two branches and this continuum here. Now it's really about what's the nature of this continuum. Okay, so we have our nice little quasiparticle here, and we have this continuum at the top, and that's actually what looks like what looks like sort of it's full of these. It turns out this is full of these molecule-like states, or dimer-like states. So it's actually, so this continuum that's sitting right above here of this branch is actually what's giving rise. I mean, this continuum has a sort of has states where you have fermions closer to the impurity, so they're sort of more strongly bound, and it's this. Once you start populating this continuum with temperature, it's this kind of physics that gives rise to this initial increase. And the other consequence, though, of having something with a larger contact, in the excited states, a larger contact tells you that the free energy is the derivative is larger, right? This is a large, so this slope here is larger here, say of these states, compared to this one as a function of 1 over A. And what this means is that this continuum, or this stuff, will actually cross your nice little quasiparticle line here at some point, as represented here. And so actually what actually happens here is that your impurity undergoes a transition, like essentially you can kind of think of it as a phase zero to quantum phase transition, although it's a single impurity really in this description, where it suddenly changes its character. So it goes from being something which resembles the bare impurity, has an overlap with the undressed impurity, where it suddenly binds a particle from the Fermi sea and forms a dimer state, or a molecule state, which is what essentially this continuum resembles, full of these kind of molecular dimer type of states. So anyway, to round this all up, okay, hang on, I even have it here, right? So at this point we have something where you have on this side you have your nice little dressed impurity, and then here it becomes bound to a particle, changes its statistics even. So it is actually kind of it is kind of something it's a qualitatively different object at this point. And so what we're arguing is actually, now coming back to this behavior as a function of temperature, this contact as a function of temperature, this non-monotonic dependence, is actually really a signature of this quantum phase transition. That will appear at an interaction, a stronger attraction away from this point. So just by measuring something at a fixed interaction as a function of temperature, this actually tells you something about what happens at zero temperature as a function of interactions. So fixed temperature, yeah. Okay, so that's, all right, is any, maybe I'll stop here and see if there are any questions about that or any comments?
Yeah, I have a question. So
yeah,
this is for the polaronic with zero momentum, am I right?
These lines here. Yes, yeah, that's right. Yes.
If we also consider finite momentum, because when we usually write the continuum of excitations, we usually write in terms the continuum in the figure with excess momentum energy. Can this picture be helpful for this case?
I mean, it's certainly true. Well, okay, so we have looked at the behavior as a function of momentum. I mean, it's certainly true that I don't know if this is answering your question, but the continuum itself will involve lots of different bound states of different momenta.
Yes.
Yes. It's just that, so I guess we're focusing on zero momenta here because that actually corresponds to the lowest energy state here. But yes, I mean, in principle, yes, you can yes, actually that's something I can probably discuss with you at some point because we are actually finishing up some work on the momentum dependence of the spectrum. So yeah, we can maybe discuss. I think you've kind of started to touch upon some other interesting features.
Okay, so,
yeah.
So this picture shows that you have crossing of the state at zero momentum. There is the state at zero momentum goes to the continuum.
Yes, goes to the continuum, which now looks the lowest edge is now a molecule at zero momentum, or this bound state at zero momentum. Yes.
So the states at finite momentum, they cross continuum earlier. Do they also?
Yes, they cross it earlier. Yes, that's right. Yeah.
I see.
Mm-hmm.
Okay, thank you.
Yeah, thanks. Okay.
Mm-hmm.
All right.
Mm-hmm.
Okay, so this is where I was telling you a little bit about the, well, essentially telling you about how looking at the temperature dependence, I can learn something about essentially the ground state of the system. Now, the final thing I wanted to talk about in my last, is it 10 minutes or so? Is the, 5-10 minutes, sorry, I won't spend too long, is this the metastable repulsive branch that we were talking about here. No, hang on. Sorry, I don't know why this is having problems today. Okay, that's not good. Okay, I'll have to use this one instead. I have a backup. Sorry, just bear with me. It's crazy, I've been teaching for months and this has never happened, but okay. All right. So, sorry, okay, so let's come back to this. So we have the repulsive branch here. So we have, so we've been focusing on this ground state here just before, but as we were discussing in the spectrum, there is all these excited states, and in particular, there's this repulsive branch that we saw, which is this quasiparticle at positive energies, which has some, manifests as a peak with some width. And it has, so it has something that it resembles like the original bare state, but now it's got some lifetime. Okay, and so this is something that's been measured both in a 3-dimensional gas and also in a confined 2-dimensional gas. Here, we have the same kind of metastable state appearing as a function of interactions. So one question has been about why is this? What determines this, the lifetime of this state? Like how, in the sense that if I, imagine I sort of put my system, so I inject my impurity into this energy state, what determines, say, the width of this, why does it actually have this width of this state? What determines how long it stays a coherent quasiparticle, how long it resembles the original state, okay? The original kind of bare impurity. So what people had originally assumed, or what have been assumed for the last 10 years or so, is that yes, clearly, this is a metastable. This width of this peak here is in this spectrum is due to the fact that it decays into these lower energy states here. Okay, so it's as you might expect, in a sort of just a simple quantum system, that's how usually you would think about it, that if there is a width to an energy level, it's because there's a decay into lower lying states. Okay, so but let me, okay, obviously I'm asking this question though, is that actually what determines this lifetime? Okay, so I'm asking this question because obviously what we're going to find is actually, well, it's a little bit more complicated than that. And so the way we did it actually is we come back to these Rabi oscillations I discussed before. So remember, so you're driving these oscillations between two different spin states, one which is strongly interacting with the Fermi gas. And we did this for two different systems. Okay, so we had the 3D gas where you have this, these interactions characterized by this scattering, 3D scattering length. And we had a 2D ytterbium gas where you parameterize the interaction slightly differently. I mean, it's not really important, but the main thing is that we actually looked at two very different systems, very different, different atoms and different, dimensionalities. And we used our theory to look at these oscillations as a function of time for different interactions. And what we found was actually we could, within a very simple theory of just including one excitation, we could actually reproduce very well what was observed in experiments. So down to the frequency and the damping and the general shape of it. Okay, within error bar. Okay, even when it was kind of becomes very messier out here. When you have very strong interactions, you start to have very overdamped oscillations, but we're still even able to vaguely capture this effect here. So across weak to strong interactions. Now yes, okay, and this is just extracting the damping, and if we extract the damping rate both from the experiment and the theory, what we see is, as a function of interaction, we find very, very good agreement. Okay, even right down to, this is going off to very weak interactions here. We, really can go down to very, several orders of magnitude. We can really capture this damping, much, much better than we actually expected. Okay, so this is the theory here, is this solid green line, including finite temperature and everything. Now, okay, the key thing here though is that the theory we use does not actually include this process where you have decay into the lower lying states. I mean, I can go into details if people are interested, but basically we don't include the right number, the right processes. You need to go to higher order in the excitations to actually be able to describe the decay from this metastable repulsive branch to the attractive states below. Okay. So what we've just learned then is that we can fit these experiments with a theory. We can fit this damping, this width of this peak, essentially. This what people thought was corresponding to decay, but however we can fit this with a theory that has none of these decay processes. Okay. So what we're finding is that actually what determines this lifetime of this quasiparticle, so how long it resembles a bare particle, how long it resembles something that that's a quasiparticle rather than something that's just something else, some many-body state or whatever, something that has very little overlap with the original state. We are arguing that actually this is what dominated by what you would call, say, what we've determined many-body dephasing rather than decay. Okay, so what do I mean by that? If we go to this little graph here, so we have our energy versus interaction. Okay, so if I sit here, so A is small, the scattering length is 0, that's actually for 0 interactions. So if I imagine I'm just gradually turning on these interactions, okay? And so this is okay, so down here we have all these, in principle, these very low energy states down here. But here, up here we have, this is our metastable, our repulsive branch here. This is our peak. It's gradually shifting up as we increase the interaction here. And what's key is that we're basically shifting up this state into this many-body continuum here. Okay, so we initially shift it up. Okay, so it has so we can even do a perturbative analysis here. But what happens, so we initially shift it up, and at lowest order, it just resembles something, it doesn't know that it's sitting in a many-body continuum. Continuum is just looking like a bare particle that's just got a higher energy. But then at higher order, actually, what we can work out is that now this state starts to couple with all these states here in this continuum and becomes broadened here. And that's actually that's what we call our many-body dephasing. So that's what actually gives rise to this width of this peak. The fact that we've pushed a state into a continuum rather than actually having this state decay into something lower down, which is very far away. Because this one we can work out, this is something that kicks in at a much higher, higher order, well, higher order in the interaction. So this occurs further along, much stronger interactions. So eventually, if you get a very strong interactions, you'll have both processes happening. You'll have both this sort of, this dephasing of this, or this sort of broadening of this peak due to this background here, and also from decay into the lower states. Okay, but certainly initially, if you're out here, it's going to be mainly dominated by just coupling to the continuum. Okay, all right. Okay, that's just a point I wanted to make. The other thing I wanted to point out is that typically, so the other way people imagine these quasiparticles losing their lifetime, or losing their integrity, if you like, or decaying, is that apart from just going decaying to some lower lying state, they imagine that they say lower their momentum. This is the actual standard way in which people think about the lifetime of quasiparticles in, say, Fermi liquid theory. If you have a quasiparticle which has a width, a peak with a width, that's because because it will decay. It's got a high momentum that will decay, or a finite momentum that will decay into a lower momentum. I just wanted to emphasize that this state that we've just talked about here, this is at zero momentum. Okay, so it's just a subtle point. So this actually is something that's qualitatively different even from any other kind of scenarios people usually think about, that gives rise to this lifetime of this kind of quasiparticle. Okay, so that's all I want to say. So we found something which is different to what people originally thought for the system, and is actually different to what is usually thought for standard theories of a many-body Fermi system. All right. Okay. So maybe I'll go to the conclusion, and then I can answer questions after this. So I just wanted to summarize then. So I've just covered how we actually prove the physics of the Fermi polaron in the system, and I've talked about how you can actually what you can learn about the nature of this quasiparticle, this Fermi polaron, looking at the temperature dependence, how that is related to a quantum phase transition, how you can even, if you're looking at this repulsive branch that I talked about here just now, how this actually has a completely different way of decaying, if you will, or dephasing compared to what people originally thought. And then there's a very interesting outlook about how, I've really focused on the behavior of a single impurity or single polaron, but there's a lot of interest in actually understanding what happens now when you have correlations or interactions between two polarons. How is this going to affect the physics of this system? Okay, so, all right, so I just thought I'd end with an acknowledgement of the group, or in particular, well, here are the main people in the quantum matter theory group in Monash is my colleague Jesper Levinson, master student Hayden Adlong, and also our postdoc Weijia Liu, who are all involved in this, as well as collaborations with experimentalists at Lens and Munich. Okay, so let me thank you for your attention, and I'm happy to take any more questions.
Yeah, we have some questions.
Mm-hmm.
Oleg, please go forward.
Mm-hmm.
Do you hear me?
Yes, yes.
Yep.
Look, I didn't quite understand the last, the width, the decay or whatever, dephasing, because to me, dephasing is decay to many body configurations. It's just semantics. I am probably missing something, right?
Well, yeah, I mean, I think the thing was that people were, I think it's about how it actually dephases in some sense. So it's just, okay. So people were either thinking that it had to be decay or into a very low-lying state, low-lying lower energy state, like these attractive branch or
So
molecular.
are you saying that instead of the hard decay, it is soft decay?
Soft decay. Well, in what sense? You mean the fact that it's...
In hard decay, you emit quantum of large energy, and in soft decay, you emit...
Yeah, okay. Yeah. But the difference is actually that it's not even just that, like normally in Fermi liquid theory, as you know, that when people, I guess you could think of that as in some sense soft decay in many cases, but there you're still imagining that the momentum, you're approximating as the momentum of the impurity changing, momentum, sort of momentum relaxation of some kind. I'm just saying this is also different from that. You have a zero momentum particle that is still got a finite width. It's still decaying into many dephasing, if you like, into a many body configuration, which is slightly different from how people had.
Yeah, but it depends on kinematics. If kinematics allow k equal to 0 decay to lower energy state, that's okay.
Yeah, but that's what people are imagining, right? That's what I'm saying. I think this usual picture is it's different to what this idea of kinematic decay.
Don't get it.
Okay, maybe we
decay is decay. Decay is decay. Of course, usually people consider the leading order. In the leading order, you have this momentum conservation. But if you go to higher orders, in principle, you can have, as soon as its energy momentum is allowed, you can have a decay at k equal to 0 state.
Right, but what state would it end up in? What kind of?
To multi-particle states.
Well, yeah, I think they.
Well,
that's the thing, right?
Particle Hall excitations, multiple particle Hall excitations.
Right, that's the thing. This is just a single particle Hall excitation. So I guess maybe we're just talking about how this is something that occurs. It's a different. I mean, you're right that if you go to high enough order, you can get all sorts of things. We're just saying that this is something that occurs at lowest order already, and it's not just the usual collisional relaxation.
Okay, so then I don't get the message. It would be probably it's interesting because it looks like you're making a generic statement, and it would be very nice to see a diagram describing.
Yes, okay, yeah, no, I admit this, well, since it's a colloquium, I was missing some details, but I'm happy to discuss a bit more in detail if you're.
Okay,
yeah.
Yeah. Formulate that it's not decay between polaronic branches, but the energy goes to the Fermi sea. It's decay to the Fermi sea.
Yeah, I mean, well, it's basically, but the impurities involved in this as well, right? But yeah, I mean, it's basically you have a continuum of states here that involve the impurity as well.
I see.
But yeah.
Okay, thank you. We have also a question from Chris Whale. Please ask.
Hi there. Can you hear me okay?
Yes, yes.
Great. Thanks for the really nice talk, Meera. I actually have two questions, but I'll ask the second one first because it relates to this topic.
Yes.
So this idea about the decay to deeply bound states was also identified as the limiting factor in attempts with cold atom experiments to realize itinerant ferromagnetism in repulsive
yes.
gases. And I know that was in the spin balanced mixtures as opposed to the kind of impurity problem that you're considering here. But do you think what you've found with the lifetime of the polaron state could have implications for quests or searches to measure or to see itinerant ferromagnetism in Fermi gases, repulsive Fermi gases?
Yeah, I think that's that's a really interesting point. Yeah, so I think exactly. So I think this does have implications for that, and it may. I think probably the key is how the system is prepared. Like I think Matteo Zaccanti had some quite interesting work where I think if you prepared it, even for a balanced case, if you prepared it in an itinerant, already kind of separated out the spins essentially. So in a kind of ferromagnetic setup. Yeah. I think what this we would argue we would suspect that what we found here would suggest that that this is actually much longer lived than people initially thought. You might have some sort of more exotic kind of excitations, and people thought, but actually, yeah, it will stay in the repulsive branch longer than people thought. Yeah.
Yeah, right. No, that's very interesting then. Yeah. Okay, yeah, we should maybe talk about that later. I don't know if I have time for one more question or if.
Sure.
Okay, just a quick question on one of the earlier points that you mentioned about the contact. So yeah, that's a good slide to show. So with the expression for the contact, the definition of the contact, if you think about integrating both sides of that, or if you take the d8 to the -1 on the other side and you integrate both sides, you can also write this in terms of like the time derivative of the free energy as a function of the time derivative of the interaction potential. So what the kind of tan dynamic sweep theorem, and that in principle should give some information about how the contact evolves in time as well. And so what I'm wondering, with these RF experiments where they've seen Rabi oscillations, and you can look at actually how the system evolves as a function of time, if you can work out anything about how the contact, or if you can sort of extract any information of how the contact is changing with time during the or from the measured data. I don't know if that's something anyone's looked at, or
I think the only one question. I mean, the only one I vaguely know of course, is this 3-body contact case, but but in Zoran's group, but I'm not sure the 2-body contact. Not sure actually. That's a good question. Actually, it would be interesting. I mean, certainly we've done some calculations of it, but yeah, the question is how would you measure it? And that's something I hadn't thought about actually. Oh, I haven't thought in detail about, but that would be interesting to think about. Yeah. Yeah,
cool. Yeah, no, I'm happy to talk about that more later as well, because it also relates to something we've done in a balanced case. But yeah, it's interesting that the RF measurements might actually have some more information.
Okay, interesting. Yeah.
Thanks.
Yeah.
Okay, thank you. Do we have any other questions? If no, let's thank you the speaker again. So only panelists could clap.
Let's see. Oh, we have one. Clap. Thanks.
Thank you for attending.
Yeah.
And Meera, thank you for great talk.
Yeah, no, thanks. Thanks, Dimitri. Yeah. All right. Okay, bye.